Peter Debye was the master architect who transformed our understanding of the invisible. By applying rigorous physical models to molecular structures, he bridged the gap between theoretical physics and practical chemistry. Observe how his work on lattice distortions and phonon oscillations allows us to predict how materials vibrate and conduct heat. By quantifying the dipole moment, Debye gave us the tools to engineer molecules with precise electrical properties. This isn't just theory, it's the foundation for modern materials science, enabling the development of everything from advanced polymers to high-performance electronics. His legacy is the ability to design our world from the atom up. This slide illustrates Peter Debye's interdisciplinary mastery, framing him as the total scientist. Key data points track his evolution from electrical engineering, practical mechanics, to experimental physics, quantum mechanics under Sommerfeld, and finally to chemistry, 1936 Nobel Prize. The visual core is the synthesis junction, showing how he dismantled artificial academic boundaries. Genius is rarely stationary. His trajectory shows a strategic migration through the world's elite scientific hubs, from the radiation pressure studies in Munich to his pivotal breakthroughs in X-ray scattering at Leipzig. This global path wasn't just a change of scenery, it was a compounding of expertise. By holding leadership positions at the Max Planck Institute and later Cornell, he didn't just participate in scientific discourse, he directed its future. His journey proves that world-class innovation requires the courage to move across borders and disciplines. This mobility allowed him to build a global legacy, transforming how we visualize molecular structures across the entire scientific community. For Peter Debye, complexity was a sign of an unfinished idea. He moved beyond mere mathematics by insisting on a concrete, visualizable basis for every theory. By stripping away irrelevancies to reach a core simplicity, he turned abstract physics into intuitive reality. Debye's famous use of a cigar to illustrate an electrical dipole reminds us that the most powerful solutions are often the most elegant. This philosophy of model building doesn't just simplify science, it accelerates discovery by making the unseen tangible. When we aim for the Debye way, we transform dense data into actionable insights, ensuring our models are not just mathematically sound, but physically true. In 1912, Debye revolutionized thermodynamics by thinking of solids not as a collection of loose atoms, but as a box holding quantized sound waves. This phonons-in-a-box model led to the Debye T-cubed law, providing the first perfect theoretical match for how materials store heat at low temperatures. The true power of this model lies in its recognition of physical limits. By introducing the Debye frequency, he accounted for the finite nature of atomic lattices. This breakthrough gives us the precision to predict thermal behavior in everything from cryogenic sensors to aerospace alloys. Debye didn't just explain heat, he defined the fundamental vibrational speed limit of matter. To solve a problem, you must first choose the right perspective. While Einstein's model was a brilliant first step, it viewed atoms in isolation, causing it to fail at low temperatures. Debye, the model builder, saw the bigger picture, an interconnected atomic lattice. By incorporating a spectrum of frequencies rather than a single fixed point, Debye achieved what pure theory could not, a perfect prediction of heat capacity near absolute zero. This shift from individual oscillators to collective elastic waves transformed our ability to engineer materials for extreme environments. It proves that accounting for connectivity and structural limits is the only way to achieve true experimental accuracy. Peter Debye didn't just study molecules, he gave us the means to measure their electrical personality. By proving that asymmetrical molecules have a permanent dipole moment, he unlocked the secrets of how matter interacts with electricity. He discovered that while electrical fields force molecules into alignment, heat works against this order, creating a measurable tension. By charting this relationship, Debye turned abstract molecular structure into a quantifiable linear slope. This breakthrough enables us to design everything from efficient insulators to the liquid crystal displays in our pockets. Today, every time we measure a Debye, we are using the very yardstick he built to navigate the molecular world. Innovation often means turning a limitation into a solution. Before 1915, X-ray diffraction was stalled by the extreme difficulty of growing perfect single crystals. Debye and Scherrer shattered this bottleneck by proving that order can be found within randomness. By using a fine powder instead of a single gem, they leveraged thousands of randomly oriented crystallites to create distinctive interference rings. This powder method democratized structural science, allowing us to identify unknown substances and analyze new materials instantly, without the need for perfect samples. Today, this technique remains the gold standard for rapid material characterization, ensuring that we can map the molecular blueprint of any solid we encounter. In 1923, Debye shattered the illusion of the free-moving ion. By applying Coulomb's law to electrolytes, he and Erich Huckel proved that ions never travel alone. They move within a cloud of opposite charges, known as the ionic atmosphere. This discovery explains the drag that slows down ionic movement, a phenomenon that old theories couldn't account for. Understanding this enterionic attraction is vital for everything from battery efficiency to biological cell signaling. By accounting for the social behavior of ions, Debye provided the definitive model for non-ideal solutions, allowing us to master the chemistry of the real world, where nothing exists in perfect isolation. In his final act, Debye mastered a new scale of existence. He realized that while X-rays reveal the atomic, visible light is the perfect tool to measure the macromolecular. By applying light scattering techniques to complex polymers, he provided the first exact method to calculate molecular weight and physical dimensions. This wasn't just a new technique, it was the birth of modern materials science. Debye single-handedly turned the study of plastics and high polymers into a precise, quantitative field. His work ensures that from life-saving medical devices to high-tech synthetics, we can engineer materials with total structural certainty. He proved that no matter the scale, a simple physical model can illuminate the most complex systems. The 1936 Nobel Prize marked a shift in the history of science. Peter Debye was honored not for a single reaction, but for giving us the eyes to see the invisible. By mastering dipole moments and diffraction, he provided the fundamental toolkit for mapping molecular architecture with mathematical certainty. This recognition proves that the greatest breakthroughs often come from providing others with better tools. Debye's legacy is a quantitative bridge between disciplines, transforming chemistry from a descriptive field into a predictive power. Because of his work, we don't just guess the shape of a molecule, we measure it. He redefined the standard for scientific discovery, moving beyond what matter is to how it is built. Integrity is often tested in the crucible of crisis. His Berlin years present a complex historical narrative, but his ultimate choice defines his character. Despite serving as director of the Max Planck Institute during a period of intense political upheaval, Debye drew a definitive line when his personal sovereignty was threatened. By refusing to trade his Dutch citizenship for German allegiance in 1939, he chose exile over complicity. This departure wasn't just a career move, it was an act of quiet defiance. His journey to the United States reminds us that true scientific leadership requires not just intellectual brilliance, but the moral courage to walk away from power when it demands the surrender of one's identity. His career may seem like a collection of separate breakthroughs, but it was actually a single, lifelong mission: mastering the architecture of interaction. Whether using X-rays to map crystals, electrical fields to define dipoles, or visible light to measure polymers, his method remained constant. By observing how external fields are disturbed by matter, he turned invisible forces into precision tools for discovery. This unified approach transformed the study of materials into an exact science. He proved that if you understand how a system responds to its environment, you can unlock its deepest structural secrets. Today, his interaction method remains the primary blueprint for how we investigate, understand, and ultimately engineer the physical world. True genius requires more than intellect. It requires humanity. Peter Debye was celebrated not just for his Nobel-winning mind, but for his vibrant spirit as an educator. He possessed the rare ability to make the invisible tangible, using simple, approachable analogies to welcome chemists into the world of physics. Beyond the lab, Debye found his greatest insights among his roses and cacti. His life reminds us that innovation isn't a 24-hour grind, it's a byproduct of a balanced life. By cultivating his gardens as carefully as his theories, he maintained the clarity needed to solve the universe's smallest mysteries. He wasn't just an architect of the unseen, he was a large-hearted mentor who proved that great science begins with a great man. Peter Debye did more than explain the world, he gave us the power to build it. By replacing qualitative guesses with exact physical laws, he moved us from a descriptive era into the materials age. His work on scattering and polarity provides the invisible framework for today's greatest innovations, from the semiconductors in our devices to the advanced polymers in our medicine. Debye proved that when we master the calculable architecture of matter, our potential for discovery becomes limitless. We aren't just observers of nature. Thanks to his legacy, we are its master architects. This is the ultimate outcome of the Debye way, a world designed with total scientific certainty.